Sure, yeah.
All right, welcome everybody for the Aerial Robotics Community Group meeting of April 24th, 2024. It's a presentation meeting, which means that we have an esteemed guest or part of this group that's going to give a nice presentation about an aerial robotic project that they're working on. But first, yeah, the agenda is going to be pretty short because it's a presentation meeting. So first going to have a couple of announcements that I want to mention first. Then we're going to have the presentation about Jay, and then the conclusion of this meeting announcing the next meeting for in 2 weeks. So first of all, a couple of announcements. As you know, like we have ROSCon in October, there have been a call for talks and workshops. So if you have any cool ROS and aerial robotics related work that you want to talk about, make sure to apply for a talk. And if it's something bigger, apply for a workshop. But it's of course a little bit more work. But just to make sure that the call for workshop is going to close soon. I think even deadline is probably next week. So just keep that in mind. Also, there's going to be the next ROS distro. Jesse is going to have a test party, which they're going to have on the 1st of May, so Wednesday. So make sure to check on Discord if you want to help the core team of ROS to test out the new distro as much as we can. I'm going to join. A couple of others that I know is going to join, so let's help them. Also, I would like to mention that I've seen some Robotics Stack Exchange questions popping up that is drone related. So I just want to ask to you all, just keep a little eye on it, and if there's any question that you can answer, please do so and help out newcomers in this field to find their way around the aerial robotics landscape. And then
quick question.
Yeah.
Have you seen any ways to get a Discord bot hooked up to Robotic Stack Exchange to automatically alert on new questions with a certain tag?
Not yet.
Anyone seen that before?
That's a great idea. Yeah.
Yeah. I don't follow it
guess,
frequently enough, so having a dedicated thread for, hey, someone tagged Aerial ROS or something would be pretty awesome.
Yeah, that will be awesome. Yeah, so that is definitely a good idea. I can ask maybe like the maintainers of the Discord group in terms of like what we can do. Maybe that's something that they don't want to do, but it would be definitely something handy. Or perhaps we can do it on maybe the aerial robotic landscape website or something like that in terms of a plugin. But very good idea, definitely. I'll probably repeat this for the next developer meeting as well. And then there's an announcement by Ryan. Yeah, if you would want to explain a little bit about this one.
Yeah, so it's going to be sort of related to what Jay's presenting today, but in working with him and Reese and developing on a lot of different kinds of systems that do path planning outdoors, I found it unnecessarily difficult to set up these environments with terrain data and make sure that all the different systems need to be using the same terrain data for the algorithms to work well, including visualization and things like that. So what I'm proposing is just I've been doing sort of an information gathering on how different parts of the ecosystem work, where they get terrain data, what they support, and what the current issues are. But anyways, I'm looking for feedback and sort of trying to figure out, what is the most important thing to try to solve first. And I'm leaning towards getting Gazebo working with terrain database rather than locally installed terrain data. So anyways, feel free to take a look at that issue. If you have experience with this sort of thing or difficulties, please provide your feedback. And then I'll probably next aerial robotics meeting, I'll present my findings if there's time, and we can select, which issue is the most important thing to solve first. And I do have some time allocated to spend to try to solve some of these problems for the community in the open source area.
Right, thanks, Ryan.
Yep.
Yeah, so these links, like I'm going to share the slides on the Discord after this meeting's over, so you can just click them right there and read more about it. So next up is a presentation by Jay terrain navigation is a project that's been working on at ETH Zurich. Yeah, I'm going to stop sharing my slides, and you can share yours.
Do you see my screen?
Yes, I can see it. Perfect. Take it away.
Great. Thanks. Yeah. So my name is Jaeyoung Lim. I'm a PhD candidate at the Autonomous Systems Lab at ETH Zurich in Switzerland. And today I'll talk about how you can navigate safely in steep alpine terrain with fixed-wing drones. So why do we even care about fixed wing? So, yeah, so fixed-wing drones, they are incredibly efficient. So this is one of the works that was done previously in the lab, where we use a solar-powered airplane to access remote glaciers and monitor them. And in contrast to multi-rotors, fixed wings can sustain extremely long periods of time, which is quite ideal for environment monitoring. For example, this specific drone can fly multiple days. And it flew, I think, a few hundred kilometers to be able to access this remote glacier, which is very hard to otherwise have people on. So for my research, I've been trying to use these fixed-wing vehicles for avalanche monitoring in the mountains, where you can access these remote locations and gather data for avalanche monitoring. So in Switzerland, avalanches are the most hazardous natural hazard. So avalanches are these sort of snow that is that accumulates and gets unstable as you have nice weather. And then it's very important that these processes are monitored and carefully understood so that we can plan infrastructure or notify people that are planning to ski on these slopes. So in Switzerland, this is done by an avalanche bulletin maintained by SLF, which is the Snow and Avalanche Research Institute in Switzerland, where they notify avalanche risk levels and provide information when they plan infrastructure. The problem is that most of the data is gathered either through, is kind of biased with accessibility, where the avalanches are either monitored through sensor stations or observers that report avalanches when they see one, or even people going up with measurement devices or even drones that inherently makes them get close to these avalanches, so they expose people to avalanche risks. So in this project called AvalMapper, the vision is that we can sort of, if a scientific domain has some potential avalanche risk areas, an autonomous fixed-wing vehicle can autonomously navigate to these interest areas, detect an avalanche, and then map the avalanche, how much volume has come down, what is the extent of the avalanche, and to understand better how avalanche processes that happen. So the project consists of these 4 building blocks, where we first need a vehicle capable of navigating through these steep alpine terrain, detecting an avalanche, navigating through these environments, detecting an avalanche, and then eventually mapping the avalanche. So the core challenge is how can we actually safely navigate through these avalanches, and then how can we actually map them? In this talk, I'll mostly focus on how can you actually safely navigate through this avalanche, these environments, which is relevant also for the terrain navigation package. So just in case if someone wants to interrupt, please feel free to do so. I should have seen this in the beginning. if you have any questions. So why is this problem challenging? So first of all, fixed-wing vehicles actually never stop. So since they use aerodynamic forces to stay airborne, they need to sustain some kind of relative velocity to the air medium they're flying, which limits their maneuverability. So they're normally limited in terms of turn radius and climb rates. So turn radius because there's limited acceleration you can generate with the while flying with a certain velocity, and climb rates because fixed-wing vehicles normally don't have thrust capable of lifting themselves, so you can only climb up to certain angles, which is quite challenging if you fly in alpine environments. As you can see, if you have sort of a maximum distance you want to not violate, and then there's the terrain that's steeper than the vehicle can climb. You need to be able to plan ahead to be able to avoid the terrain. This is quite challenging if you're operating the vehicle manually, because you might not be in a collision yet, but you might not be able to avoid a collision later. And recently, there has been a change of regulations where that, especially in the EU, that you have to be within 120 meters from the terrain, which is for fixed-wing vehicles. For a 2-3 meter wingspan, you normally have a turn radius of 60 to 80 meters, which basically means that you cannot do a full loiter within the distance constraint. So you have to be able to plan ahead to be able to safely navigate in these environments. So a good analogy is that I call this a fixed wing in a corridor problem, where if you are checking collisions in a receding horizon manner and you're flying along a corridor, since fixed wings can fly straight, everything looks fine. But as you approach the end of the corridor, you realize there's a dead end, and that you cannot avoid a collision anymore because the fixed wing vehicle cannot turn inside the corridor, or the corridor is too narrow. So the question is, how can we ensure safety for this kind of dynamically constrained system to be able to operate safely in alpine environments? So this kind of concept is not so new. So a lot of this has been addressed in robotics. We call it the inevitable collision states. So you can think of a point mass that can only decelerate or needs a certain stopping distance to stop, maybe because of limited acceleration. And so even if the sort of wall or collision states are smaller for a dynamic system, it has an effect that your sort of states that you cannot avoid a collision, we call it inevitable collision state, extends outside of the obstacle. And this has been sort of in consideration for a long time for a lot of vehicles, vehicle types, especially multicopters or ships that have limited maneuverabilities. And the key point is that sort of this kind of, you cannot guarantee that you will not go into an inevitable collision state with a receding horizon or a finite horizon collisions check. So you basically need infinite horizon collision checks to ensure that to determine whether you are in an inevitable collision state or not. And a good way to approximate whether you can to determine whether you're in an inevitable collision state is to use periodic paths, because you can just check collisions within one period, and then you can be sure that you will not be in a collision in the future as long as you stay in this periodic path. So then you can have a conservative estimate of inevitable collision states. So then we can basically use this kind of loiter maneuver, which is... Sorry, yeah, go ahead.
Hey, sorry. Yeah, I was just asking, especially with these infinite horizon kind of approaches, doesn't the staleness of the terrain data become a factor where you're trying to plan? But I mean, I don't know how recent is the terrain data, especially when you're trying to go out in such spaces where you're monitoring for avalanches. Doesn't how fresh the data is start affecting your trajectory planning capabilities, where you have so much to account for?
Yes, so that's correct. So I think for this work, the main assumption is that you know the terrain geometry. I think it's a good point that maybe the terrain data itself might not be that accurate, but then there's a lot of factors in there because it depends on what kind of source you use, right? So you could have generated the terrain data from a previous mission that you first map the environment accurately and then use it for sort of this kind of navigation, or you could actually take conservative bounds of, like how tall trees are, and then take into account the terrain uncertainty so that you can avoid the terrain. But for this work, the main assumption is that you already know the terrain geometry. It's more about how can you handle this kind of non-dynamic effects of inevitable collision states and plan safely through while considering the kinematic constraints of the fixed-wing vehicle.
And has there been prior work, or is it a sound approach to maybe do some sort of simultaneous mapping as well as the path checking or obstacle avoidance that you're doing? Or is the problem intractable simply because of the scales at which you operate and limited compute and factors such as that? That you need
So
like a
there
dedicated mapping mission.
So there is already
Go ahead.
quite some prior work on doing simultational or real-time mapping or localization. I think recently the hot topic is geolocalization with only using images, but that is not being addressed in part of this project. If
Thank
that
you.
answers
Yeah.
your question. Yeah. Yeah, so we can use these kind of terminal loiter manners. So as long as the end of the current maneuver ends with a loiter, we can be sure that our path doesn't result in an inevitable collision state. So we only need to check the safety, whether we can safely reach the loiter and whether the loiter actually is safe, and then we can conservatively check whether it's in an inevitable collision state or not. So the idea of the terrain navigation project is that we sort of pre-compute using the terrain geometry whether you can fit a loiter or whether there is a valid loiter position or not given a specific radius. So we pre-compute whether the center of the loiter is going to be whether a loiter exists or not, and then basically formulate it into a more conventional planning problem where we already verified the terminal state is going to be safe, and then it becomes back to a normal path planning problem. So to make this pre-computation efficient, we can first think of these two kind of constraints where we need to comply with the regulation, the maximum distance, which is 120 meters in Europe or EU, and then the minimum collision surface, which is, you can think of it as a margin that we want to take into account the terrain uncertainty, which is 50 meters for the real, I'll show you later. And then we can see whether a planar loiter will fit, where the surface of the loiter centers will fit. So you can sort of horizontally offset the distance surface with these loiters, and then create this kind of dotted surface, and then do the same for the maximum surface. And then, as you can see, when the surface where the green dotted surface comes below the yellow dotted line, there is actually no safe loiter position that can fit within these constraints. So you can use this principle to compute very efficiently, given the terrain data, which places you can loiter and which places you cannot. So as you can see, this is Dishma Valley in Davos, which shows a steep valley. And this is the Gotthard Pass, one of the major passes that connects Switzerland and Italy, and you can pre-compute these sort of safety of the loiter positions and plan a path through it. You can also see that the planned path actually traverses through this unsafe state. So it just means that you cannot stop or loiter there, but you might be able to still traverse it within the kinematic constraints. So we can now, since we already verified the safety of the terminal loiters, we can solve it as a regular path planning problem. So for the experiments I'm showing, we use 120 meters for the maximum distance, 50 meters for the minimum distance, because trees are normally less than 30 meters tall. And for the target avalanche applications, there is actually very little buildings. And then we want to solve a path planning problem to satisfy the kinematic constraints, which is defined as the minimum turn radius and the flight path angle. And we can just use regular sampling-based planners like an RT star or a bit star to find the kinematically feasible connections between the start state or loiter to the goal state loiter. To model the dynamic constraints, we use we call it the Dubin space, where the distance in the space is defined as a Dubin's distance. So Dubins show that a curvature constrained shortest path consists of these six kind of a sequence of arcs, straight lines, and arcs, and then it is a subset of these six path types. One of the ways to make this sort of more efficient is you can use a Dubin set classification method, where the conventional method is to exhaustively go through all six path types and take the shortest one. But you can take the Dubin set classification method, where you can determine which subset of path types would be optimal depending on the start and goal configurations. So for sampling-based planners, this actually speeds up the process quite a lot. One of the things that was addressed in the terrain navigation package was the original Dubin set classification was actually wrong, because the actual mathematical proof had some issues. So as you can see, the sort of vanilla Dubin set classification methods wrongly classify some of the path types if you compare it with the exhaustive method. So so this was corrected. It was actually published as a workshop paper, and then got merged to OMPL, where we could show that the fixes done for the Dubin set classification and terrain navigation is necessary, and it also speeds up the Dubin set classification method almost 2 times, which results in a much faster discovery of the feasible paths. So we test our planner in these 3 sort of example methods. One shows sort of flat terrain, the other a narrow valley, and then the most challenging example, which navigates through the Gotthard Pass. So you can see that the planner effectively can find safe paths between 2 loiter positions. What's also interesting is that the convergence time of these 3 sort of examples, which extends 12 by 8 kilometers, are less than it's less than 30 seconds. So it means that the planner is able to find a close to optimal solution within a single loiter cycle for a small fixed wing vehicle. You can see that for the Gotthard Pass, within a few hundred seconds, the path is not fully converged, but it still finds a safe path, so you can still follow the path and be able to reach the goal safely. It might not just be as optimal, and you could also potentially replan as you traverse the environment. And also these kind of pre-computed safe loiter cycles are also useful for operational use cases of fixed wing. So this is while the vehicle is traversing the environment, you can actually abort the mission. And it's actually quite tricky to, you cannot just abort the mission if you're traversing through steep terrain. But since we already know which places you can safely place a loiter, we can just sample through the pre-computed valid loiter space and choose a rally point as dynamically as you abort the mission. So we test this on a tilt rotor VTOL vehicle, and which has a mission computer on board. So the mission computer runs the sort of the terrain navigation planner package, and is connected to an FMU for, in our case, a PICSOC4, which sends the instantaneous path references to the path tracking controller. And the from the ground control station, the operator sends dynamically positions that are dynamically evaluated and planned to navigate the terrain. So this is a video of us testing the vehicle in Riemenstalden in Switzerland under a narrow valley. So on the left, you can see that the vehicle always stays within the distance constraints while navigating dynamically to various positions and also staying dynamically feasible. So this is one of sort of the first demonstration of an autonomous fixed-wing vehicle operating in steep terrain within the low altitude limit. Yes. So this is just sort of a summary plot of what you saw on the video. So you can see that the sort of planned references always stay within the distance constraint towards the terrain, and can navigate through these different loiters safely. And this is the distance to the terrain of the vehicle, and you can see it always stays between 50 and 120 meters. One of the things is that this is what you have seen is the planned reference. So it doesn't mean that the vehicle never violates the constraints. So you can see that because we use Dubin's paths as a reference, the curvature is discontinuous. So it's actually not dynamic. It's kinematically feasible in terms of curvature and climb rate constraints, but the vehicle cannot change its roll angle instantaneously. So you see these sort of big curvature jumps. In this case, the largest was close to 15 meters, and it happened when after a huge descent, the vehicle tried to climb and turn at the same time. So we were a bit lucky that the vehicle actually didn't violate the distance constraints, as it was happening on a relatively flat place in the terrain, but it doesn't guarantee that the vehicle will stay within the regular. This is one of the future works that we would like to address, that how can you sort of make the tracking performance better so that we can actually minimize the tracking error, but also bound it so that we can guarantee that it will always stay within the regulations. So this is just sort of a demonstration of it flying through mountain passes. So you've already seen Gotthard Pass. This is one flying through Furka Pass. So you can see that the blue overlay is the sort of valid regions where you can plan a loiter, and then plan a path. And then eventually the vehicle follows it and is able to traverse this kind of mountain valleys. So this, so we can fly through navigate through these mountain valleys. So now I've been trying to use this for what we actually care about, mapping avalanches. So this was actually just last week where we used this kind of terrain navigation to reach an avalanche interest region and then try to actively map it, and then also try to sort of safely abort the mission, come back to the original home position, and things like that. So this has been published in, I think, a few weeks ago in RAL, and it's the code is available at under our lab organization and GitHub. Ryan and Reese, who is in this call, have been adding support to ROS 2, so I would like to say thank you, and hopefully a lot of people would be interested in using it. And to process the sort of terrain data, there's also a separate package called GridMapGeo, where you can use TIFF files to load and visualize your terrain data for downstream applications that are used for planning. And you can also align multiple DEMs or load terrain from the VRT server, which Ryan has been working on, which is you can have an online server that contains large-scale terrain. For example, the SRTM dataset has elevation data of the whole Earth, so you can dynamically load terrain data and then be able to plan through these environments. So thank you for listening. If you have any questions, I'm happy to answer them.
Thanks a lot, Jay. I just also shared the GitHub links to both projects.
Thanks,
so if
yeah.
anybody has some more questions for Jay, just go ahead and raise your hand or just say it or mention it in the chat. Mayank, go first.
Really cool videos, man. I mean, the live demos are really nice to see. Have you ever had instances where the vehicle was lost and you had to trek a lot and recover it, or like any potentially unsafe errors beyond the tracking error you showed?
So not after the planner is running, but in the beginning of my PhD, I actually had an incident where the vehicle crashed into an avalanche terrain, so we had to get a helicopter to rescue it because we couldn't trek up because obviously it's an avalanche risk terrain. But it turned out it was a bug in the guidance controller and not necessarily. It was actually before I wanted to test the sort of default guidance controller before I try out my planner, but it crashed before. So it also shows how kind of challenging on the sort of mission planning aspect to make sure the vehicle is going to operate safely. So in this case, it was you normally plan waypoints in a sequence of lines, so you actually don't know what the vehicle is going to do in between. And I, of course, tested everything in simulation, but the real vehicle behaved slightly differently. So I think it's very hard to also judge how close the vehicle is to the terrain, especially if you're against a very steep terrain. So yes, I had crashes.
Thanks for that. Maybe one other quick question. You mentioned how the actuation limits of the craft limited like how good your tracking could be and things like that. Was it also sometimes that the GPS or the sensing that you had on board would not support you as well because of how challenging the terrain is, like with multipath issues and stuff like that, which sometimes GPS becomes prone to in such mountainous regions? Like, was sensing also ever a factor that it caused, even though your planning was perfect, but like the actual behavior of the craft was borderline unsafe or some issues like that because of sensing issues?
Not really. So GPS is actually quite good, and I think multipath issues are not in general a problem as long as you are within a safe distance to the terrain. So I think it happens more if you're either too close to a cliff or under vegetation, for example. So I think, at least for my experience, I think this was one of the concerns we had, but this is not what I experienced during the tests, at least for this project.
Great, thanks.
All right, I think
Thank
next
you.
up is Khaled. Go for it. Hello?
Yeah, hi, thank you, Kim. Really nice work, Jay. I
Thank you.
just have a few questions. First one is, where do you mentioned that you were using a mission computer, correct me if I'm wrong.
Mhm.
Yeah,
Yes.
so all the algorithms were kind of were working from this mission computer. There was no connection with the ground station, or the mission was not, the data was not processed over the ground station.
Exactly. So all the planning and navigation was done on the onboard computer. We have an Intel NUC, and then we have connection to the ground station, but it's for visualization and monitoring. And also the operator, which was me, but the operator commands the target position or sort of high-level commands, but the whole planning and navigation was done on the computer,
Yeah.
onboard the computer.
Yeah, and it was connected to a flight controller that is based on microcontrollers.
Yes, so in this case, it was using a PICSOC4 running PX4.
Yeah, that was the question. Yeah, thank you for that. And your application is based on ROS2 or based on or?
So it's based on ROS1.
Yeah.
Part of the reason is that we had some issues with ROS2 over LTE. So, for example, the DEM also gets loaded on the vehicle and sent over to the ground station, and we had some networking issues, I think. So that's, we have an implementation, and I think Reese and Ryan also was the sort of who were actually moving it to ROS2. I also tried on my side, but for the operation workflow we had, I couldn't get it to work reliably. So.
More than perfect, Jay and Ryan. You did a great job. So yeah, applaud for you. Well done.
Thanks.
All right. I saw that Tim, you had your hand up, but I don't know if you still want to ask your question or if your question was already answered.
No, my question was answered. Thanks, Khaled.
Ah, okay, perfect. Then I'll, yeah, Ryan, go for it.
Cool, yeah. So I was just curious, do you think there's any aspects of the terrain navigation inevitable collision state that could be applied to a short or long fail-safe action and run on an embedded microcontroller in case you don't have a companion computer? The situation I have is I'm flying in steep terrain and really close and flying along it, and then I have a fail-safe because my radio link goes out. And the autopilot needs to choose, like, if I'm going away from myself, it usually wants to turn around. But if it turns left, it's going to head terrain. If it turns right, it's free. Given that autopilots generally already support terrain data, do you think that there's any, minimized versions of these algorithms that could be run just for that initial fail-safe action?
So I think it depends whether you want to comply with the maximum distance constraints or not. So once you have the maximum distance constraint, your planning problem becomes extremely, your feasible phase becomes very unconvex. So it actually becomes a problem that you cannot solve with a closed form or a low power compute. So that's why we use sampling-based planners to solve it. If you are fine with it violating the maximum distance constraints, I think you can do quite a lot. You can have a lot of choices because you're just trying to move away from the surface, which is, so I think another option is you can or I've been interested in trying to look into this kind of safety filter approaches where you can try to evaluate safety in sort of a kind of a predictive way, in a model predictive control, which is quite popular to run on embedded systems. I guess it depends on also what kind of embedded system you're talking about. But yeah, so I think there are quite some choices. I have been also interested in trying to do this a bit more reactively so that you have another layer of safety. But yeah, I think it's quite open. But I think if you try to comply with the maximum altitude constraints, it's actually quite challenging.
Got it. Thank you.
All right. I think, yeah, we have one more question. Yogesh, go for it.
Yeah. Hi, Jane. Great presentation. I have just one question. Like, do you consider avoiding obstacles which are in the planned path? Is there any sensing capability on board?
Could you repeat the plant? Or
It's like once you have a planned path and there is a dynamic obstacle that might. Yeah. So, is there any sensor on board to avoid such obstacles?
So there's actually not. So it's actually a very hard problem if you try to. So what's missing from this work is dealing with sort of this kind of uncertainty of the terrain or obstacles, whether it be dynamic obstacles or unknown obstacles. The problem is it's very hard to guarantee safety if you only partially observe the obstacle on the path, because you don't know outside your sensing range what the geometry of this obstacle is going to be. So this would be quite an interesting problem to solve, but currently, as far as I know, there is no really good sensor choice that gives you the quality of the depth or range that is light enough to not be a primary payload on a fixed wing. So like the sort of automotive or the LiDAR sensors use it for automotive applications. They have quite some sufficient range, but they're quite heavy to put on a fixed wing. So you might be able to fit one, but you might not be able to fit a camera anymore, for example. So it's an interesting problem, but yet to be solved.
Okay. Thank you.
All right. So do we have any more questions for Jaeyoung? Please, go for it.
One more question, and it sort of relates to what Ryan asked as well. So given the pre-compute part where you've worked out where the valid regions are, if you have that data, do you know at any given point in your flight, do you know where the next safe loiter position is, or is that an additional calculation?
So you actually do.
Right.
So it's basically a 2D array with, you can either store it binary, like yes, no.
Yep.
What I do currently is I take the average between the, if there exists a safe loiter position, I take the average between the maximum and minimum altitude to have maximum clearance, and that is actually advantageous for the operator because you don't need to specify the altitude anymore, so it makes it a 2D goal command.
Yep.
And that way, yeah, you can get decent, or it's enough to compute on an embedded system. The problem is a safe path to connect to that loiter, is hard to compute. So if you just do Dubin's path, which is you can do it quite efficiently on an embedded system, you can't guarantee that it complies with the altitude, and then to do that you have to solve a separate planning problem again.
But as an intermediate step, sort of to solve Ryan's problem, if you had the pre-computed valid reasons, because given the terrain, given a terrain data, you would know that, so you could potentially have that tiled and loaded up as well. you could have something which is better than what we have at the moment. It still may that may still violate conditions, but at least would potentially send you in the right direction. So the issue is not so much you'd hit the cliff. It's you might violate your oh yeah, you still might, because you depending if the loiter requires that you construct a more complicated path. If your loiter is not within an easy sort of easy direction. Yeah.
Exactly. Yeah.
Yeah. But would that be worth having, or is it still? I guess you need to have a look at examples to determine whether it's worth the effort to do that.
So I think my answer would be probably yes, because now for me, frankly, it's almost impossible to operate a fixed wing safely without running SITL and looking at it, how it works. And in emergencies, I think having this kind of high level, like I really want to like just find the safest place now, so you can buy a bit of time, so you can also take evading action on top. So I think for this project, it was more constructed in a more academic way. How can we guarantee safety? I guess there is some value in, and this like kind of prior, I think I find it quite useful, but it's also, you will, I think, find a lot of corner cases where it will collide into the terrain, and maybe you can also pre-compute the sort of this collision surfaces and use Ryan's line of sight computation. That might help, but I guess it depends on the terrain also, how complex the terrain geometry is. And
Yep. Okay. No, that's that's really helpful. Thanks.
Thanks.
All right. Next up is Alexis. Go for it.
Hey, great presentation, Jaeyoung. Nice to meet you. And I was wondering if you think that this is a good starting point for more like different environments, like for example, to study landslides in more tropical and hot, warmer weathers, because I know that this is for the nature of the environment that you are working on, it's more like how can I say, more empty. What do you think that they will? What kind of problems will search for your approach once we want to move it into that context?
Yeah, thanks. So I think it's a good question. So first of all, the planning itself is not that specific to avalanches, because it's more of like trying to be able to operate fixed wings close to the terrain and navigate through it. The problem I can see is that currently we don't deal with unknown obstacles. So that's where the 50-meter sort of margin comes from, where we sort of have this conservative bound where we sort of injected knowledge of like the bound of where the obstacles are going to be. In Switzerland, the alpine environments, it's normally 30 meters of trees. But I think for tropical environments or whatever other natural environment, depending on how uncertain you are on the geometry of the environment, I think you would need a bit more to be able to handle like tall trees or artificial objects like buildings. So one thing is I use digital elevation maps, which are quite easily available in sort of these geographic information systems. But it doesn't include any vegetation or building. So I guess in more other environments where this can be more relevant, I think you would either need to be able to dynamically sense these unknown obstacles and try to deal with it in some way, so as long as the assumptions align, I think it would be directly applicable, but whether these assumptions are valid, I think it's the more what we need to consider.
yeah, of course, it will add a lot of complexity to it. But yeah, thank you. I think that this is a good step in the right direction. So yeah, probably someone will add that soon or later.
Yeah, thanks.
All right.
Thank you.
I think we probably can default the question. If anybody has some additional questions, I would advise you to ask it either on the Discord channel or on the Discord thread or email Jay. But thanks a lot for your presentation. It's great to see the work. Also, we've already heard it, of course, of through the work that has been done, also in together with Ryan and Reese. But it's nice to also actually see the results of your hard work and risking your lives for Avalanche. But it's really cool.
Yeah.
Thank you a lot. All right, let me just share my slides again. My arm is a bit occupied because my cat suddenly decided that she needed cuddles, so she's here on my lap. Let's see. So just I just want to add a slide here for the reminders to do for the subcommittees. So so that you will update your projects and have something to tell about on the next developer meeting, at least that we're going to have in 2 weeks. So for simulation to define a bit more precise goals. Outdoor navigation, there's also a couple of ones there at least, and indoor navigation, determine the standard environment and simulation to work with. Documentation, we're working on the website. But just let's not have too much of a discussion here. I'm just kind of like setting it here as a reminder. So let's have the discussion, of course, on the Discord channel for that. So the next meeting is on the 8th of May. So at 4 p.m. UTC. The 1 May is the Jesse tutorial party. For 8th of May is the next Aerial ROS community group meeting for developers and subcommittees. So the GitHub organization is github.com/ROS-Aerial, and that's the location of the aerial robotics landscape. So you can add some more information for that, or add yourself as a member. And that's pretty much it. I would like to thank you all for joining, and see you in 2 weeks.
Thank you, Kim. Bye-bye.
Thank you.
Thanks,
Thank you.
Kim.
Bye-bye.
Bye.
Thank you.
Bye.
Bye.